Hello, welcome in week 12. I'd like to cover mostly the counters, but I'd like to make brief comments on shift registers as well. So let's talk first shift registers. Registers, as you may remember, are the fastest, the most expensive, but the fastest pieces of memory being used mostly in CPUs. For shift registers, they are being used to store and transfer of data in general in digital systems. Register in general is used for storing and shifting data, which means ones and zeros, and which you enter to and from external sources. The most basic register is a D flip-flop, as you remember. It is triggered by clock slope. In this case, on the figure 8, 1 by positive clock slope. If we supply 1 to the input D, input data, at the positive clock slope, output is set to 1. If N remains 1 until we reset, so it is a memory, piece of memory, 1-bit memory. If we supply 0, if we supply 0 and then the clock positive slope, output remains 0 and remains as long as we change it. So they are obvious memories. So we may have several types of shift registers. As you may see, let's make it a little bit bigger. Yes. So we may have serial in shift and write serial out. We may have shift in, shift left serial out. We may have parallel in, serial out, and a bit more, as you may see on this figure. We won't cover all of them. Just a couple of examples. Let's have serial in, serial out, shift register. As you may see on figure 8.3, it's for D flip-flop. What is special here is the fact that the system is synchronous, which means all clocks, all input clocks are acting at the same time. They are connected. So let's have serial data input at the leftmost side of the picture, and let's have serial data output at the rightmost position. The first flip-flop, flip-flop 0, is at the leftmost position, and flip-flop 3 is at the rightmost position here. So let's have an example of entering enable 1010 in the weighted order, which means rightmost bit is least significant, LSB, and leftmost is MSB. So let's enter LSB first, which means here in this example it would be 0. And let's assume that the register initially is clear. So we enter 0, then 1, then 0, and then 1. The table 8.1 shows the content of flip-flops from FF0 to FF3. The upper row shows the initial values of the outputs of those flip-flops, which are all 0. So we enter first 0 to flip-flop 0. The rest is 0. Then we enter next 1, and FF0 becomes 1, while the 0 from flip-flop 0 is now shifted to flip-flop 1. the remaining flip-flops are still zeros. Then the next bit is a 0, so this bit takes position in flip-flop 0, and flip-flop 0 and flip-flop 1 now are being moved to flip-flop 1 and flip-flop 2. Then we enter the most significant bit 1, and this one is setting flip-flop 0, and the remaining flip-flops are shifted to the right. As a result, we obtain 1010 as the output of flip-flops FF0 to FF3. You may remember that at the input nibble, Q0 was the least significant bit. Q3 was most significant bit. But don't be mistaken, those symbols, Q3, Q2, Q1, Q0 now have different meaning. But order of the bits, initial data is the same. So we have 1010. So in serial data, one bit at a time is transferred. If you want to get out data of the register, the bits must be shifted serially to the Q3 output. Let's have another example. Example 8.1, 5-bit register. The register is initially clear to 0, and let's have input nibble. Sorry, it's not nibble, it's just 5-bit from Q4 to Q0, 11010. And let's see what's happening during 5 clock pulses. So we enter here differently as it was previously. We enter first most significant bit. So we enter 1, 1, 0, 1, 0. And then using this shift register, we move the bits to the right, and as a result, we obtain the same order. Q0 is least significant bit, and Q4 is most significant bit. The difference was such that we entered starting with leftmost bit, most significant bit. We may have, as you remember, serial in, parallel out, shift register, and this is an example on figure 8.6. This is a synchronous clock, so synchronous system, all clocks act synchronously. And let's have an example. We enter 0110. New bits substitute the initial ones. So the initial values contain all ones, as you can see, and then we enter 0110. As a result, we move the first 0 to the right. When we enter 1 in the second clock, this one is put to Q0, then Q0 obtains another one, and then 0. So this is the order, 0110, and those are the values of the flip-flop 0. At the second clock, we enter 1, and now second flip-flop is 0, moved from flip-flop 0, and then flip-flop 0 is 1. We enter another one, and at the clock 3, we have sequence 110, and finally we have 0110. And this nibble is sent to the out in this order, Q0, Q2, Q1, Q2, Q3, but this is a parallel output. Example of existing hardware. Let's have parallel in serial out shift register. it requires some help of gates, AND gates, and OR gates. In parallel out shift register example, simple one with no problem with any additional hardware. We don't cover bidirectional shift registers. It was just a short comment about the existence of shift registers. Let's now comment on the counters. Counters obviously represent, in general, in the theory of computer science, finite state machines. What are they? So we have several types. The most classical are Moore machines and mini machines with they are equivalent, although some description is slightly different from each other. Let's have an example of finite state machine. Such can be a turnstile machine which is being used in subways. How does it work? Turnstile machine may be locked or unlocked. So if a machine is locked, we enter a coin, it is unlocked. If we push unlocked machine, it's locked again. So the output is none. If the machine is unlocked, we put a coin, next state is unlocked. If we have unlocked machine, we push, it is locked. So the next customer cannot enter without entering the coin. The state diagram of such turnstile machines is here. So we have two states, locked and unlocked. If we push machine, so the push is an input acting on the locked, it's back to locked, doesn't help. Pushing the locked machine does not help at all. If the machine is unlocked, we enter the coin, it's still unlocked. If the machine is unlocked, we can enter, we push, and then the machine is locked behind. If the machine is locked but we put the coin is an input acting on the state locked, the machine is unlocked. We push and then machine is back locked. So this was mechanical example of finite state machine. We may have more mathematical description. So finite automaton machine may be deterministic automaton, for instance, and it is a 5-tuple. It has R, sigma, delta, Q0, F, where R is a set of states, sigma are transitions, inputs. We act with inputs on this machine, on states. Then we have a transition function, which means what's happening, to what state the transition happens if we start with certain state and we act with certain inputs or transitions. We have start state, we have certain accept state or not. So certain example for operating system, you have the graph of the system in which we have 4 states, we have inputs. So the first state was 1100, we act with the input PS and we have new state and so on. The description of such transitions may be included in a table, and such table describes the transition function in which we have next state. So we have at the leftmost position, leftmost column, we have initial state, we have inputs, transitions, P of Q, P of S, V of Q, V of S, whatever it is. And when we, on the crossing of this row, certain row and certain column, we have inside of the table, we have next state, which means, for instance, if the initial state was 110 in the first row, and we acted with input P, the next state was 1000. If the initial state was, for example, 1000, and we acted with P of Q, the next state is 0010. So content of the cells of this table are next state. Certain cells include the symbol of zero set, null set, which means that transitions are not possible. So coming back again, such a state machine may be described by the 5 tuple in which we have states, we have inputs, we have transition function, and so on, and simple, very simple graphical representation in form of the graph. So when we count to counters, they belong to the group of finite state machines, so in which we have initial state, we have maybe clock signal acting as the input, and then we have next state. So let's have asynchronous counters, in which we have flip-flops which do not change their states exactly in the same time, because they don't have common clock pulse. Let's have a 2-bit asynchronous binary counter, for instance, built as on figure 9.4, built on 2 D flip-flops. As you may see, those D flip-flops are triggered by a positive clock slope. And as you may see, if we have initial state Q00, therefore not Q is 1, and this one is feedback to D0, and when the clock comes with its positive slope, obviously the next state will be 1, because this is how the D flip-flop works, which means 1, and the output, but not output, not Q0, will be 0, which is now at the input. So the next clock acting on this flip-flop, the first one, would now reset the flip-flop to 0. So as you may see, the leftmost flip-flop, FF0, will change every clock, every positive slope of the clock. Now the output, negative output, not Q0, is connected to the flip-flop 1. And now again, its positive slope will trigger the flip-flop 1. However, because this happens, the positive slope happens at the output of the first flip-flop every second clock, so the second flip-flop FF1 will be set every second clock. Let's see the timing diagram, which explains a lot. So we have on top, we have clocks 1, 2, 3, and 4. We have also Q0. So as you can see, Q0 is changing its state at every clock positive slope. So we have 1, then 0, then 1, then 0. Change happens at every clock. Now, because not Q0 is changing its state every second clock, as you see, those positive Q0s may affect the flip-flop 2, therefore the flip-flop 2 is changing every second clock. So you may see what's happening. If we start with 0, 0, first clock is causing the Q0, Q1 to be 0, 1. Next clock is causing the flip-flops Q1, Q0 to be 1, 0. and then 1 1, and then back 0 0. So it looks like a counter: 0 0 0 1 1 0 1 1, and back 0 0. So this is a 2-bit counter indeed. And again, what's happening in table 9.1, it's a binary state sequence. So the first state of the counters Q1, Q0 is 0, 0. The next is 0, 1, then 1, 0, then 1, 1, then 0, 0, corresponding to decimal numbers 0, 1, 2, 3, and back recycles to 0. We may connect 3 D flip-flops and have 3-bit binary counter, which act to each other. One flip-flop is affecting another exactly the same way as the previous example has shown. So we have 3 D flip-flops, and inputs are connected to the first one connected to clock. The second flip-flop 1, clock is connected to the output not Q0, and the flip-flop 2, the clock is connected to the previous Q1 not. So per analogium, the same history, and this is why this clock is able to count from 0, 0, 0 to 1, 1, 1, from 0 to 7. Important here is that we have a delay. So obviously the clock, leftmost clock, the clock at the input of FF0 obviously does not affect flip-flop 1 or flip-flop 2. Before the clock of flip-flop 1 is affected, which means output of the flip-flop 0 is delayed compared to clock. So every next clock is delayed compared to the previous one. This is why the counter acts in series. Not all of them change at the same time. They act from left to right. Let's have 4 bits asynchronous binary counter made of D flip-flops. Now they are triggered by negative edge of the clock. So we start with all zeros, and then instead of at the output we have now Q0 instead of not Q0. The next flip-flop is connected with the previous one by output Q. Not Q, but Q. So the flip-flop 1 is connected to flip-flop 0 by the Q0 of the first flip-flop, and so on. Previous example was different. They were triggered by positive slope of C, and connection of the next flip-flop was with the negative, the output of the previous flip-flop. So now connection is slightly different, but it's acting exactly the same way. It is a counter. If you want to create asynchronous decade counter, so let's have a modulo 10, okay, which means from 0 to 9. We need to force the counter to recycle before 10 appears. So we have partial decoding, which means we have the means which cause that at the 10th clock we get back to 0. Let's see how it is working. So we have 4 D flip-flops. All of them have feedback from negative output back to data input for every flip-flop. We have clock which is triggered with negative slope, and at every negative slope of clock, the Q0 is changing its state. So first the clock is causing Q0 to become 1, second is causing Q0 to be 0, and so on and so on. And now, as it was in previous ones, in previous counters, the negative slope of every output is causing change of the state of every next. So, and in the moment of Q1, this Q1 is changed when Q0 is producing negative slope, and so on and so on. This way, Q1 is changing its state every second clock. What's happening when the clock 10 is coming? You may see that we have here NAND gate connected to Q1 and Q3. When the Q1 and Q3, as you can see here, okay, when Q1 and Q3, you may see here, okay, if they produce 0, which means if both are 1, the output will be 0. Clear is clearing the whole clock, whole counter. So whenever Q1 and Q3 are 1, as you may see here, Q1 and Q3 are 1 here, okay, which is 1010, which is decimal 10. So when we have the situation when Q1 and Q3 want to become 1, the whole counter is sending active low clear signal, which is clearing the whole counter. So it doesn't produce 10, it's just producing 0 on all flip-flops. So this is a glitch. So the value wanted to become 1010, but before it's coming to reality, because Q1 and Q3 are trying to be 1, at this moment the clear signal is being created and clears the whole counter to all zeros. So you may see that at clock 10, negative slope of clock 10, the glitch happens because Q1 cannot become 1. And back to 0. The whole counter is cleared. We may have counter using JK flip-flops, which may even be simpler than using D flip-flops, because we don't have feedback here. As you may see, the counter built on the JK have short circuit inputs J and K. Every flip-flop and its input J and K, those J and K are connected together and connected to high, which means they are always 1. J and K in every flip-flop are 1. What does it mean? It means that whenever negative slope of clock happens, we have toggle. We toggle, okay? Which means we change the state. So when you see the timing diagram and the first clock happens and its negative slope, the slope happens, Q0 is toggling from 0 to 1. At second clock, the same, Q0, flip-flop 0 is toggling from 1 to 0, and so on and so on. At every clock, Q0 is changing its state. And when the flip-flop is changing its state, it's affecting next clock of the next flip-flop. And again, for instance, when Q0 is producing negative slope after clock 2, Q1, next flip-flop, is toggling. And then at Q4, at clock 4, when the negative slope happens, Q0 is producing negative slope, and Q1 is toggling, and so on and so on. Now, what's happening with our 12 decoder? So let's have an end. Whenever Q2 and Q3 become 1 altogether, they produce 0 as the output of NAND, which means active low clear signal is 0, then it's clearing clocks or flip-flops FF2 and FF3. Okay, so instead of having 12, we have glitch at the situation when Q2 and Q3 when Q2 is willing to become 1, both are 1, Q2 and Q3 are 1, then they stop obtaining number 12, instead we have 11, because flip-flops F2 and FF3 become 0. By the way, when you see at FF0 and FF1, flip-flops are not clear. They are never clear till only Q2, Q3, which prevents the number to become 12. Instead of becoming 12 because of this glitch, because of the clear signal, they become 0. The whole counter is reset to all zeros. Another type of counters are synchronous counter, when all flip-flops are clocked at the same time by common clock pulse. Let's have JK flip-flops here, and again the situation is easy because, as you may see, J and K, both inputs in both flip-flops are connected together, and the leftmost flip-flop is connected to high signal, to 1, which means it's set up for a toggle, and the rightmost flip-flop, FF1, is connected to Q0, to the output of the previous flip-flop. Now clocks are common. So whenever a clock is positive, has a positive slope, the flip-flop is toggling. If the FF0 is always toggling, FF1 is toggling only if Q0 is 1. So the clock input goes to each flip-flop in this synchronous counter. And still the delay is helping in acting correctly by this counter. Let's have 3-bit synchronous binary counter. And what's happening, we have toggling, of course. The FF0 is being toggled at every positive slope, so every clock is changing the state of FF0. FF1 is changing its state every second. Q0, as you see, whenever Q0 has the correct slope, is changing its state. And we have AND gate. AND gate is connected to Q0, Q1. What does it mean? If both Q0 and Q1 are 1, we toggle Q2. Okay, so why is it so? We have to take a look on this situation. So we have 3 binary flip-flops from 000 to 111, and you may see that when the clock 3 comes, we have Q0 and Q1 both are 1. As you may see that at clock 3 we need to change Q2. So if Q0 and Q1 are 1, we have to toggle Q2 for the first time from 0 to 1. The next toggling of Q2 happens at clock 7 because we have Q0, Q1 is 1, and we need to toggle Q2 from 1 to 0. So those two situations are the only situations in which we toggle Q2. In both cases, it happens when Q0 and Q1 are 1. So this is why we have this kind of hardware solution. Again, the same story here with more details. Let's have now example of 4-bit synchronous binary counter, 4-bit now. And again, the same story because JK is connected, the FF0 is connected for toggle, and every flip-flop is toggling whenever JK signals are 1. So those flip-flops are negative clock slope triggered, and we have a situation that flip-flop 2 is toggling when Q0 and Q1 are 1. Flip-flop F3 is toggled when Q0, Q1, and Q2, 3 of them, are 1. When you look at the timing diagram in which every next flip-flop is changing its state every second clock, every fourth, and every eighth, and so on, you may see that the sequence of outputs requires this toggling. So we need to toggle when we switch from 3 to 4. Okay. So when we have 1, 2, 3, and then 4, we have negative slopes, and the inputs are changing. So the FF2 is changing when Q0 and Q1 are 1, F3 is changing when Q0, Q1, and Q3 are 1. And it happens in 3 occasions. So Q0 and Q1 are causing toggling FF2 at clock 3 and clock 7. And clock, no, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 11, okay? So you may see. And then we change, we flip-flop, we toggle FF3 when the outputs Q0, Q1, and Q2 are 1 at the same time, which happens twice in calculation of the counter. In decade counter, it happens the same. We need to know when to toggle the next flip-flop. When you have the sequence of all states, and if you want to avoid 10, you have to toggle at 9. We will come to design of synchronous counter next week. So this will be all for today, and we will get back to counters, synchronous counters, and their design next week. Thank you very much.